Well, good morning and welcome to another edition of STAT2402. How are you this morning? How are the assessments going? The tests, are they okay? Too hard, too easy?
Good.
What about the last one? How was the first test? Okay? The second one, which is due last Friday, wasn't it? Not too bad? No, not too bad? Not too good? Reasonable? Can manage? And the one due this Friday? Has anybody looked at it yet? Not looked at it? You haven't looked at it yet? Don't worry, there's still a few days to go, right? But yeah, should look at it early. It's not that bad because it comes very fast after the last one. So there's only one question in there, but the next three that will be in the next half of the semester, as I was saying, becomes more substantial. Now we're doing some real work from this week. What we've done so far would have been largely classed as revision for somebody who's done some first year tests maybe. Some of it wasn't quite revision, but yes, only small extensions. Now we're getting to the real part where we're starting to look at some models, some meaningful models. So while you can get the test this week, let's do this week, is looking at a data set in one way, but if you look at the data set, you'll find there's more information there than we could possibly use in some of the analysis we're doing up till now. But now we have regression models. We can start looking at them in more detail and get more information from the models. And so we'll see how this works today. And towards the end, I hope I can show you a video this week. Maybe next week we'll see another video just to see how things work out with data modeling. But this week will be something else. So we're looking now at some regression models. The problem is this, as we will see as we go through. Here's the example we'll look at here. This is the Donner Party tragedy many years ago, where the party here got stranded in the mountains, and the rescuers, by the time they got to them, many of the members hadn't survived. And so the idea here is to work out whether the survival attributes of those who did survive depends in some way on who they were. So whether they were the age to start off with, and whether they were men or women. And these things are of interest not just to anthropologists, but also to human biologists and medicine and medical people as well, as to whether gender makes a difference in survival things. Later we'll take a look at another data set to do with survival as well, and that will be part of the assignment you'll be doing, or the assessment you'll be doing afterwards. So the idea here was whether females were better equipped to deal with stress. How many think yes? No? Girls? You don't think you're better equipped for stress? How many think girls have a more stressful life? You reckon? I reckon so, absolutely. Women have a far stressful life. Regardless of what we say about equity and all the rest of it, hey, by and large, women do more work than men do. Yeah? In the house, outside, as parenting, they do far more than men do. It should be like that, actually. Luckily for me, I've been able to spend quite a bit of time with my kids when they were younger, although now I'm away from them at the moment. Yeah, it's women actually very, very capable of dealing with stress. Not every woman, of course, not every man either is the other way around, but by and large, they seem to be better at this. So here's the data, and it's in the library Sleuth, which comes with the book. So you can take a look to what's going on here. So there are two commands you will find in R that we use, the with and the within. So what the with does is, with the data set you've got here, it looks underneath that. So if I say, for example, in this case, my data is Donna, I say with Donna, I can say summary of what are the variables. So by that I can take a look at what's underneath that and refer to the variable by name. So looks like age is here a variable, so I can say with Donna summary of age. It gives me summary of age by itself. Of course, you can also do summary of age by referring to the thing directly. So we've got summary of Donna $age. You've seen that before. And some of you might have seen the command attach as well. If I attach Donna, then I can refer to all the variables underneath it by name directly. The thing with attach is you must also detach it afterwards, after you've done with this. So you can detach donor, otherwise you'll have that flowing around in your memory. You don't want that to happen, to clutter memory up, and other reasons as well. But the better way is not to attach these days. The style is not to attach this and then work within that as you work through. So with or within. So within here, I'm defining some variables. So I'm defining this thing called survival, which is the status minus 1. So the status here would have been something like yes or no, survived or not, if you look at the data directly. And I've converted it to numeric. So yes or no, when you go to numeric, becomes 1, 2. Yeah, even then down to 0, 1. That's why the minus 1 is there. And the 6 here is now as numeric, again is 2 minus as numeric. So have a look to see what's going on there as numeric when you convert 6 to that. It again is now down to going to be 1, 0 after you've taken this away. So the 6 here would have been 1, 0, and now is going to be, well, as numeric be 1, 0 now. So have a look at the data directly as it is, and then see what's going on here. So the summary of the data is given to you over here. So the interest here is in survival, and I've converted that from yes, no, as I said earlier, to 1, 0, and this is what I need to model the binary outcome as survival. It's not good as yes or no because that's categorical. I wanted binary for logistic regression modeling here. Okay, so exploration data, this is just a plot of the survival versus age and the survival versus, so they've got 3 pieces of information. I've got the survival and age here, but also it's color coded by male, female. This is a clever way of doing things. Often you can put more than 3 bits of information. So if I have, so for example, with age and survival here, so okay, I've got male, female there. But if I have something else here as well in the data with this particular the subjects I'm looking at. So the data you will see later on I'll present to you probably with the next assignment or somewhere. I'll deal quite a bit with the education stuff as well. So a data where I've got, say, the marks of students versus the number of classes they attend, one of my favorite things, and I can plot that. So I've got the classes attended, the mark there, that's all clear enough, but I can also then color code the thing by grade, for example. And instead of using the plotting symbol, the default, I can actually put the actual mark on there. So I can put more information there than I need to, than I can otherwise. Or I can have the grade there as a code, as A, B, whatever, HD, whatever else, and I can color code the thing with gender. So all those kinds of things I can do to make my graphs more informative. Here it's clear to see from there, it looks okay, but the problem is the way R plots things. If you've got 2 data points that coincide, it plots them one on top of the other, and you can't tell them apart. So the next plot's exactly the same with a bit of jitter put in there. So I've actually, what that does is move things along a little bit. And so you can see more clearly here that, for example, this data point was 1 in the last one. Yeah, 1 dot there, 1 circle. Now it's actually 2 there. It's also jitters the top one as well. As you can see, overall, it looks like more females have survived here than males. And looking at the age, though, you might tend to look and see, well, maybe the female is a bit younger. It's not so clear here. Good enough males here as well. So age mightn't be such a problem here. They seem to be okay. More males may be the older end than females. But you can adjust for age. That's the whole idea. You want to adjust for age and then see whether gender has a difference in survival. And you can't do that if you do a simple analysis by looking at the things that contingency table. The model here is binary, so we have the ith individual here in the party. The survival is yi, where yi is 1 or 0. 1 means they survive, and 0 means they don't survive. Probability of survival is pi, and so it's more properly should be not pi but pi I, because the survival depends on the individual's characteristics, which will be age and gender in this case. The pi, in other words, the pi for survival isn't fixed in this case. It varies with the particular subject you're looking at. So we'll get to that later on. And so here my yi is Bernoulli with the probability mass function as given there. So if yi is 0, that means the person hasn't survived. That means that part becomes 1, and I'm left with probability of 1 minus pi. And if yi is 1, then that part becomes, this is for yi equals 0. And if yi is equal to 1, then I've got the pi to the power 1 there, and the other part becomes 1. So that works out as you expect it to work out. And so the usual idea here, what we have here in the Bernoulli case is we know the mean is going to be pi and the variance is pi times 1 take pi. This is a problem because we know, we saw this before last week actually, that the variance here depends on pi as well, which is a problem. As pi goes to the ends, the variance decreases. It comes in the middle, the variance increases. We want to adjust for that in some way. So what we've done so far is single proportion, use hypothesis testing using contingency tables and those kinds of ideas, or hypothesis test for single proportion and difference of proportions and all those kinds of things we've done in the last few weeks or so. What we've got here is something different. Those things, while they do give information, don't allow lots of other things. So chi-squared, for example, I require that the expected frequency in each cell needs to be at least 5. This isn't always the case, especially when I've got low counts in data. And the other problem, of course, the major problem is I can't invoke, or I can't look at the effect. Yeah, I can't look at the effect of the other variables. So I might be able to say, for example, that two variables are independent, or the odds ratio I can work out in some way, but I can't actually nail the effect. What is the effect of age, for example? If somebody is 10 years older, what is the effect as far as probability of survival goes? If I'm looking at males versus females, all I can say is that the survival is not independent of gender. I can't actually put a number to it. And that's the kind of thing I want to do over here. And so, as I was saying earlier, I can look at odds ratios for males and females, but that's really all. I can look at the thing with respect to class as well, and the other things as well, whether the percentage of crew member and so on and so forth. So these kinds of things is what I'm after here. So I'm really after some kind of regression model that quantifies all this for me. The problem with the usual normal regression case that you would have met before, and we met earlier in the sessions here, is that the assumption there is that the observations are normal with some mean and some variance. The mu I here is what we model here. So the expected value or the mean depends on the subject's characteristics. In a simple case, it just is a simple linear function of another variable xi. So the expected value of subject I, with the mean value here, is just a single straight line, beta naught plus beta 1 xi. If I have more variables, as we saw with the fish data, you add more variables to it, you've got more effects in there. Other than that, we're expecting here, the model is the mean value is given by this straight line. But of course here, the issue is the mean here can be positive or negative. It can take any value essentially, in principle, or at least intervals of values. And this is okay because we are having here the yi as being continuous. The issue with the Bernoulli case is that I don't have that. I had required to have my pi i's to be between 0 and 1. I can't go outside that range. That's one real problem there. And that should be less than or equal to 1 here. I've missed a little thing there. So less than or equal to 1. So that's the real issue here. So a model like this one, as we have for the normal case, where I've got EYI given my covariance is just beta naught plus beta 1 xi, can have values outside this range. So I can't allow that because then I've got a nonsensical model. And in fact, you'll be surprised at the number of people who actually do exactly this kind of thing with count data. By Bernoulli, they do this kind of normal regression. What a pile of rubbish that is. I'll say it in public. It's a pile of rubbish. There's no information there at all that's of any use. But people do it all the time. And mainly, I'll say it again loudly, many people who do this are what people who call themselves data scientists. All they know is computer science, not much stats, and they make all kinds of rubbish stuff. Makes absolutely no sense. It's a pile, it's very bad indeed. I am sure you guys won't do it because you're learning something here that's useful. But many others out there discover these things by themselves, make mistakes all over the place. So in this case, I do want to take a look at the effect of sex and age as far as survival is concerned. And the thing with linearity is, in other words, the models that say beta naught plus beta 1 x1 plus beta 2 x2 and so on, these linear additive models are very useful. They're simple and they are nice and easy to interpret as well. But we still want to make sure that we have the values between 0 and 1. So the thing to do here is we go back to the odds idea, and the odds we know behave themselves very well, so we want to model that instead. So here we're looking at the odds here of survival versus not survival, And so the log of that is more interesting, because the log, as we saw earlier, was it last week or so, tends to become more like a normal distribution. And the other idea here is that it does take values in the continuum of the real numbers, negative infinity to infinity. So as pi goes towards 1, I'm going to have 1 upon 0 here, essentially. That goes towards infinity. And if pi goes towards 0, this log part, the thing in the log goes towards 0, and log of 0 goes to negative infinity. So the logit function here, the log of the odds, is perfect as something that I can model using my usual regression, because it does satisfy this idea of having a range that is in the real numbers here. And so here's a quick plot of the logit function itself. As pi goes to 0, it goes to negative infinity, and it goes to 1 there. But more than that, it's nice and very, very well behaved, especially in the middle there. It goes through 0 when we were 0.5. So 0.5 essentially is the chance of survival being 0.5 means essentially it's random, like tossing a coin essentially. It's purely random in that case, and that makes sense. Logit of 0 means there's no effect at all of this variable, it's random, but it does behave itself quite nicely in the middle as well. And if I take a look at the model in this case, so my model is not for pi I anymore, it's for the log of the odds. So log of pi I over 1 minus pi I, there's beta naught plus beta 1x. If I invert that, it's not so hard to do if you've got some facility with exponential functions. The first thing is to remember the log requires me to take exponentials of both sides, so it's e to the power. So that means that my pi I, and I think I must have done the thing before, later somewhere. Anyway, it might be there. We'll see later on. So pi I over 1 minus pi I becomes exponential, or e to the power, of this thing beta naught plus beta 1xi. And then I just have to solve for pi I from there. It's not so hard actually, it's just essentially a thing that looks like the x over x plus 1 minus x. So I've got something like x over 1 minus x is equal to y, and I can call this whole thing y for the moment. Then I get x is equal to y times 1 minus x. And here this is just y minus yx. Take the y across to the other side, I get x plus yx equals y. Factorize the x out, I get x times 1 plus y equals y. And so my x is going to be y over 1 plus y, and that's all I've got here. It's y plus 1 over y over 1 plus y. So there's my y of 1 plus that thing. Now the pi I is less than 1 and bigger than 0, as you expect, because exponential is always going to be positive, and the top line here is less than the bottom line. That means this thing is always positive, but always less than 1 as well. Perfectly behaved as I expect it to, so the model behaves itself as I would like it to. So the thing we do is, this mean part here is often in notation senses looked at more generally. So this is more mathematical ideas, which is not of the major interest to us, but if you look at this kind of thing later on, you might find this function neta coming in there, and that is the linear part, or the expected value part of it. So we write this as exponential of this linear part, or the expected value, over 1 plus exponential of that. And so overall, this is our model. This function gi, which is in this case log of the odds, is called a link function. You might find this later on if you look at this kind of models afterwards. And so a plot of the linear predictor against the actual value here of pi looks like this. As we go to negative infinity, it goes towards 0. The other way, it goes towards 1. Nice and smooth. At 0 is equal to at pi at 0, when the mean is equal to 0, I get pi is 0.5, which, as I was saying earlier, really means this is random. Then the model is as we had it before. My yi is binomial. Probability of success here is pi I. Probability of failure is 1 minus pi I for the ith individual. Probability mass function is given before, and my pi I here by my model is given to me in this exponential form there. All good so far. Now the coefficients of regression, if I've got p covariates, then I've got p of these things plus 1, because I've got the beta naught as well. So I've got beta naught till beta p as my coefficients of regression, and there are many ways to estimate these things. One of the most common is what we call maximum likelihood. We'll see the ideas afterwards. and maximum likelihood estimators have some very nice qualities and properties that are useful, and we'll see them again in the last half of the course. So don't worry about this yet. The machine will do this all for us. The model here for the donor party in that case is the log or the logit of the odds. Logit here, the log of the odds over here of survival, and the variables I've got are age and sex. For individual I, you can see here the pi I depends on I, which is the individual, his or her age and his or her gender. And if I reverse that, I can write the pi I in terms of what I had before, exactly the same as we had before. So that's all good. And what we do in R is we require this function GLM. This is called Generalized Linear Model. And if you had before, we looked at, say, models for normal data, what we used was LM as whatever. So my response here would be, say, Y versus my X1 and my X2, whatever my variables here were. And I'd have my data frame here as well, data equals. That's what required there. So here I need a bit more. So I need GLM as my generalized linear model function. And what I get out of this is, again, an object, which is a GLM object. I can call the thing anything I like, but usually we use things like .glm1, and then if I change the model by reducing it or adding more things, it becomes GLM2, 3, 4. I have a record of all those things I can compare against each other as I go through here. So I require here, the status here is my binary survival 1-0 case. I've got the age of the person and the sex of the person. I have the donor is my data frame here, but I do require something else here. Because it's GLM, R doesn't know what you're looking at. What are you talking about here? Because this GLM applies to more than just binomial data. So I'm going to specify here my family is binomial. Now in the bracket here it says link is logit. Now as I say here, that's the default for binomial. For binomial, logit is the default link, the most used link. So you can actually omit that if you wish, just have family equals binomial, that is good enough. And that's what you'll find I'll do often enough. I won't have the link there specified directly, it's not required. So I've saved the object in the analysis object of the results in donor.glm1. Now, as you will realize, this actually contains quite a bit of information. If you look at, say, like any other data frame or any other object, if I look at names of this thing, then it will tell me what's stored underneath it. And underneath it stored, you will find at least things like residuals. Now, if you look at the things we had a look at earlier with Fisher's exact test, look at Fisher's exact test, underneath you'll find residuals. Look at chi-squared test, underneath you'll find residuals. I think that's coming up in the next test, if I'm not mistaken. So you can find those things from there. You'll find coefficients as well. You'll find p-values, the whole lot. You can access them individually if you know how to do those kinds of things. So there are various link functions with the GLM function in R, and I'm not going to be looking at any of them in detail. The one that's important for is binomial here, and the default link is logit, although you can use other links as well. The Gaussian link also works here with identity, which essentially is going to be exactly the same as LM, no difference there. We'll ignore everything else here, but we will look at Poisson because that's another thing we look at afterwards. Poisson there, and there's something also called quasi and binary and Poisson. That's used in some instances. There's also another one that actually is a negative binomial model. We'll see afterwards. Negative, which is something else we'll do afterwards. But the main thing for us is that there are many link functions. Binomial is the one you will be using for binary data. Poisson later for count data. We will see some quasi ones as well later on. So that's why it's important to specify which one you mean here. So this is an important class of models, the GLMs here, that apply to count data. Now, count in case binary or Poisson are both counts in some sense. Binary essentially has a level 1-0 count. Poisson can be more than that. So both of these is where we will be using this kind of idea and this kind of regression analysis. Output of the model in the same way as before here. Now here what I've done is, as you're aware, that in the case of regression for categorical variables, R will use one of the levels as reference. By default, it will be in the order, alphabetical order here. So sex, of course, is female, then male. What we've done is we put male as reference, so I can see the difference between males and females as an extra for the female. So the reference has been set to male here. Have a look at this to see how you can do that yourself. So it's a relevel command here for this particular variable sex, and I've put the reference as male here. Then the GLM command over here and the output. So it looks very similar to the other outputs that we've seen with R and linear models. The first thing is it tells you what you've actually fitted here. It gives you the call function here and the model you actually have fitted here. It gives you this thing called deviance residuals. In other places you might find residuals there as well. Then it gives you the actual model output in as far as the fit is concerned. It gives you the coefficients and the p-values of interest to you. It then in the end gives you some other values for model diagnostics, if you like, or fit of model. It gives you this idea of null deviance here and also gives you this idea of residual deviance. So the null deviance corresponds to the null model, where your hypotheses essentially are that the age coefficient and the sex coefficients are 0, right? Null model. So in this case, it's going to be H naught is beta for, let me call this beta 1, beta 2. It says they're both equal to 0. And H1 says, no, that's not the case. They're not both 0. In other words, at least one of them is not 0, is what the other model H1 says, as the model has been fitted there. So what it gives us here is the residual deviance is what you get under H1. When you fit the model, that's what you get. And the difference in deviance is an idea of how well your model actually fits. And we'll see that afterwards. So here the difference in deviance is about 10 or so. Now the other thing you will see is degrees of freedom here. So the null model has degrees of freedom 44, and the residual deviance model under the H1, the fitted model, has degrees of freedom 2, less than that. So the difference here is 2, and that's because you actually have fitted 2 variables in the model. So you've got this variable for age and sex. So it's got those 2 degrees of freedom less now. And we'll see how this works later on to see what we can do with it. The other thing you'll see here, this archaic information criteria here, there's also another model fit parameter or quantity we can look at afterwards. Now with both of these, the AIC and the residual deviance, the lower the better. So residual essentially is again this idea of misfit. The lower the better. The lower residuals are, the better the model fits. And AIC is also some of that kind of thing. It's actually based on likelihood, but it's a bit better than likelihood, because usually if you add more variables to the model, your likelihood will not increase. It will decrease. The same with deviance here. If you add more variables to the model, your residual variance won't increase. It will decrease, at least, or stay the same. The AIC is a bit different because if you add more variables, it penalizes you for a model with more variables than with fewer variables. Now, if you're interested, you might find, and we might look at the formula for this kind of idea sometime later on, but essentially it's the same as likelihood, but then it adds or subtracts the number of variables you fit into the model, so it makes it a little bit worse if you've got more variables. So that's the output here. The most interesting thing, of course, is the first box over here with coefficients and the p-values to indicate to us which of those particular variables actually is a significant effect here. So it's clear from here what's going on. The estimate for beta 1, which is the age, is actually negative 0.0780. 820, and is significant at the 5% level. So as I'm saying over here, all the tests here, of course, now are two-sided by default. So the p-value we'll consider is going to be 0.05. And so here we're saying beta 1 isn't 0. In fact, it's negative. I can see that. If it's not 0, it must be positive or negative. And beta 2, the effect of sex here is positive. So that straight to me, the positive shows me straight away that the females have a higher survival than males. And we can quantify that as we go through here. Now, of course, the intercept is just 1.6. The intercept is not significant, but it doesn't matter because the intercept is always going to be in the model unless there's a reason to drop it. Unless you've got a reason based on the context to omit the intercept, and you can force R to omit the intercept, it'll always stay in the model. Whether anything else is significant or not, and whether it itself is significant or not, it stays in the model. It's just a mean adjustment, if you like. Okay, stop there for a second. Any questions? All good? So here, we know the model equation. What we had was, we had log of the odds here is what we modeled here. So I can actually find the probability here of survival based on the model equation. And you can see what's going on here. I've got exactly the same on the bottom and the top, except I've got the extra 1 plus on the bottom. But I'm after here the difference in, say, males and females as to what it looks like as far as the log of the odds is concerned, and then quantify that. So here is a plot of the males and females. And you can see what's going on here. So as far as the males and females are concerned, the age is something that's continuous, and the age will make a difference to both of them. But you see, sex is going to be taking the value 1 for females and 0 for males. So when I have a male person, this particular term drops off, yeah, the 1.59, because sex is either 0 or 1. If it's 0, that means it's a male person. 1 means a female person. So when it's 1 for a female person, that is in the model. If it's 0, it drops out. And you can see what's going on here. Females have a higher probability of survival than males in this case. Now this second line is actually curved. Yes, you can see they're both curved. But by looking at the graph here, there's actually a fair difference between males and females as far as survival probability goes from this model we've got here. And they both, of course, decline with age. So the model mean and variance here, well, the mean is going to be just pi, and the variance is pi times 1 minus pi. And I've got the expression for pi there, so I can work it out from there. We're not going to do it over here, but you see, this is how it works out. So the variance here also depends on pi, unlike the Gaussian case where the mean and variance can be quite independent of each other, and they are, unless there's some other dependence that we haven't considered. So here, this is the situation. We have in the Gaussian cases, it says we assume a constant variance. That's not the case here, because of course as pi changes for different individuals, so will the variance change. So here, that's part of the model. Quantifying these things, so we're looking at the ratio, the odds in this case, which is the pi I over 1 take pi I, is given by the exponential form, and this is essentially going backwards to right to the odds here in exponential form by taking exponentials, and from there you can solve for pi as we did earlier. You can take a look at the ratio, the odds ratio for 2 particular individuals. So here's the odds ratio for 2 particular individuals, yeah. And if I've got that, looking at, say, simple linear regression, in this case, what I've got over here, simple regression, with 1 variable here for the log odds, then if I have a difference of, well, if I have A for the first individual and B for the second individual, then what I've got over here is, for the first individual, the odds is pi A over 1 take pi A, and for the second is pi B over 1 take pi B. The model equation tells me the exponential of beta naught plus beta 1 A for the first, divide by the same with the B in there for the variable value. Now, the way exponentials work is if I divide them, that means I subtract the actual exponents here. So the beta naughts cancel off, and the beta 1 A and beta 1 B, if I subtract, I get beta 1 times A minus B. What I'm getting here is, for 2 individuals who differ in the variable that I've got here by an amount A minus B, the ratio, the odds ratio, is exponential of beta 1 times A minus B. That's a very nice and simple interpretation here. So the odds ratio is going to be this number here. if I change by the change in the variable is 1 unit increase, that's a positive change. That means you can see what's going on here. If that changes by 1, if that change or difference is 1, I've got exponential beta 1 here. So that means the odds ratio is going to be x of beta 1. In other words, the odds ratio is x beta 1, which means that the odds of one is x beta 1 times the odds of the other. You can see what's going on here, and we'll see how that works out in practice. Now, this is assuming, of course, that all the other ones are fixed. So if I keep age the same, and for the same age individuals, I want to see whether the males have, or females have an advantage over males for survival, I can do that. Now, what happens if I have a change of more than 1? Well, you see, if the b minus a minus b is more than 1, then this becomes x of, if this is 2, for example, I get 2 beta 1. And by rules of exponents, what this actually means is that's going to be x of beta 1 squared. The difference is 3, it's cubed. The difference is 10, it's to the power 10. It goes up by powers, yeah? Makes it far worse, as you can see here, as I look at this. So if I'm looking at, for example, 2 individuals, both female, one is 10 years older, then the probability or the odds ratio here becomes whatever this is to the power 10. X over the beta being the coefficient, to the power 10. And that can make a difference, as we'll see later on. That's interpretation here. We interpret things in terms of the odds ratio, which will be x of beta 1 here, where beta 1 is my coefficient, for a unit change in that particular variable. Now this is tricky because often people get this wrong. For the case of the donor data set here, so the odds of female male, for example, if I've got 2 people of the same age, then the coefficient for sex there, yeah, it's for female in that case, above the male, because the model here, as we know, had male as reference, so the coefficient here is extra for the female. So there it is. For a female person, I have a 1, which means in the model, which means is 1 times the beta 1 here, or the beta there. But for a male person, that's 0. So the difference between males and females, as far as the odds ratio is concerned, is x to the power 1.597. That's 4.9 times. So the odds of a female surviving is 4.94 times the odds of a male surviving. That is massive. Now, if you read in literature, you might find this in sometimes the newspapers or articles, whatever else, saying that this particular drug or whatever treatment improves the survival chances or the odds of survival by 4 or 10 or whatever. Or if you smoke, your odds of cancer is increased by 10-fold. That kind of stuff is what this comes from. This is where it comes from. This kind of argument and this kind of analysis over here. So females are more likely to survive. In fact, the odds of survival for the females is almost 5 times that for males of the same age. Yeah, that's the crucial thing here, assuming the age doesn't change. As far as age is concerned, look at, say, males or females, doesn't matter, either one of the same, of males and females, and you look at the difference in age here. So for a unit, the parameter there, well, the coefficient was negative 0.0782, and x of that is about 0.92 or so, which means that for a year increase in age, the odds of survival will be 92%. In other words, it's going to decrease by 8%. Yeah, I'll say it again. If you, for increase of 1 year in age, the odds of survival decrease by a factor of 0.9248. In other words, the odds of survival will be 92% of the odds of survival for someone a year younger. Or if you like, the odds of survival decrease by almost 8% here. Is 7.52%. So a year older, the odds of survival decrease by 7.52%. If you look at a 10-year difference here for either males or females, as long as they have the same gender, then as we said earlier, it becomes 10 times that, or it becomes a power of 10. So now the odds of survival are going to be 54% for somebody 10 years younger, right? So if you go up 10 years in age, your odds of survival is 54%. Or if, sorry, 45%. Apologies. 45%. So odds of survival now is 45% if you're 10 years older compared to somebody who is 10 years younger than you. Or if you like, the decrease in survival is 54.2%. Odds of survival decreases by 54.2%. Survival, there's a V missing here. Any questions with that? You've got to see the right kind of words over here, otherwise things don't make sense. Yeah. If I say something like the chance of survival is less, that's fine. But I'm not actually going to compute the probability here. In all of this, we have not computed probabilities of survival. We've looked at the odds and ratios of these things. What's the odds of survival for a male compared with a female? And what's the odds of survival for a person younger compared to older? Any questions with this? All right, so if you do look at the next assignment test questions, you will find that it references a paper. Pick it up and read it. Pick up the paper and read it. Now, what you'll find is what I've done in the paper and what I've asked for are different things, which is okay. But if you read the paper, you get some idea of how these things need to be written up, because all the analysis is there. And in the end, as I keep saying, you've got to write something in terms that makes sense in the context and to the person who works in the area. In other words, you can explain this in such words that a lay person can understand it. Most people don't understand odds. They understand chance of survival, those kind of things. If you say the chance of survival is, or the survival is decreased by 42% or whatever, that can make sense to them. So if I make calculations here for the actual pi, you can see I can do that, no problems. I would individual I here for a particular age. I'm taking age 45, and for a female person, probability of survival is 0.428. For a male person, same age, probability of survival is 0.132. Excuse me. So once I have the pi's, I can work out odds of survival for each of those individuals, and I can work out the odds ratio. There is the odds for survival for the female person and for the male person. And I can take the ratio, 4.94, the same as I had before. So I can repeat the calculations directly if I wish, but of course, why would you bother doing that when you've got the answers straight away from your output in R? All right, any questions so far? Well, that's just about the lot of it. That's the major part of what we're doing today here. Nothing much more than that, really. The R output contains these things as well, so we know this from the other R outputs. It always gives you similar things in regression analysis. You've got standard error here in one column. You've got the Z value. The probability of Z bigger than or equal to Z absolute value gives you a two-sided p-value for a two-sided test of beta j equals 0 versus beta j not equal to 0. And you can calculate directly if you wish. Otherwise, you can look at the p-value yourself. No problems with that. It's in the R output. Maximum likelihood estimators have some nice properties, as we said earlier. They usually are unbiased, not always, but they're usually unbiased. It's a nice property here, and you can actually obtain standard errors for them. And there's this thing called efficiency in statistics. So efficiency is in some ways how well do they actually do the estimation. And the other important thing for us is that the estimates actually have an approximately normal distribution, and that's where we get this Z test from. Approximately normal distribution, we can find probabilities from Z test. So if we go further into this mathematical ideas over here, you can say that this thing is essentially the beta j's here, the estimates are normally distributed with some value beta j, which is the mean, which is unbiased essentially. So on average, the average value of this thing is equal to what you're trying to estimate. And there's some variance here which comes from calculations if you want to. It doesn't really matter. But for the moment, we know it's available to us in R, and it gives us p-values as well. Test in the usual way here. you can do this usual calculation. The observed value of the z statistic is going to be the beta you observed over the standard error, which is in the R columns, and you can find a two-sided p-value. All those calculations are given here. Not very important or interesting for me because, as I say, you can get them straight from R anyway. So here is the standard error. The z value here is just going to be, for example, take a look at this one. That will be your observed value of 1.59729 upon its standard error, which is 0.7. 0.75547. And that is equal to this 2.114. And then I obtain from there the p-value as being equal to, essentially the z value is positive, says z bigger than this 2.114, and it's doubled because it's a two-sided test. That's all that's happening here. You can do it by hand if you wish, and I think it's been done by hand in the slides, although, as I said, not very interesting for us. And there's a full model if you want. I've got, sorry, that was the last model. Now, one other interesting thing is that often variables will have interactions. It mightn't be just sex or age that makes a difference to survival, but maybe that together have a difference as well. And so we include this extra term here, which is age times sex, essentially, interaction term. Now we want to test to see whether this provides a better model or not. And it's just a matter of now including that in my model. So I've got this age with sex that way. So this is my age term, my sex term, and age-sex interaction. Of course, I can do it in one go by putting in simply age with a star 6, as you would have seen before, my application in R. And so it fits me that model. It gives me the usual term for the main effects of age, the main effects of sex, and then the interaction term. You can find what's happened with the interaction term is now my age is no longer significant, and neither is this. It's 0.08, so 10% is significant, but it's not significant at 5% level. And so I would, in this case, by looking at just p-values over there, we would decide that the interaction term was not significant. All this is doing is plotting the thing together again as before. So I'm plotting over here by making the grid and actually calculating the values of the probabilities by the formula using my coefficients, the male, female. Again, it's similar, the female looks similar, the male looks more straight. It's not straight, actually, it is curved, slight curvature there. You might be able to pick it up if you look at it carefully or put a ruler to it, you'll find it's the case. But again, females are a higher probability of success of survival than males, as we had before. But the main thing is the interaction term is not significant, and you can look at this by looking at the p-value from the test. And these are calculations for it. It doesn't matter because I get my p-value straight from R. Look at the slide if you wish. This is the calculation by hand for p-value, but I have the p-value from R, and essentially all this is doing is plotting the whole thing to see that probability in the tails, what I'm getting over here as my p-value. But I know the p-value from R is given to me, and it's not significant. And so I'll, in other words, my the model with the interaction term is not significant. In other words, the interaction term is insignificant. I can drop that. My last model is better than this one here. And we'll see later on how we can compare models in other ways as well. As far as the confidence intervals are concerned, I can actually calculate them in R, and we'll see how to do that at some stage. But here you can calculate them in the usual way. The observed value of the thing you're trying to estimate is 95% over here. So it's plus or minus 1.96 times the standard error. This is the usual way of finding confidence intervals. The point estimate, 1.96 times the standard error, plus or minus if it's 95%. So that can be done as well, and R can give this to you as well. So here's a calculation for that. Not very interesting, as I say. You can get this from R. You would normally bother doing it this way unless it's in a test or exam or somewhere you should show it by hand. So given all that stuff, I'll skip those slides. And essentially this is going to confirm what your hypothesis test said. You'll find that the significant coefficients, when they're significant, the values will actually lie in the 95% confidence interval, otherwise they won't. And so that you can test by looking at the thing yourself. Let's get to this drop-in deviance idea. So the drop-in deviance idea is similar to the AIC and the BIC we'll see after all. And similar to the F test you have seen before in ANOVA, it gives you an overall assessment of one model versus the other model, or one model itself, to see whether there's anything in the model that's significant here. But it doesn't actually give you an idea of what variables in the model are significant. So constrained and full, be careful with what you are looking at here. The constrained is which is the one that actually corresponds to H naught, the null hypothesis, because you're constraining things to be 0 there, right? You're restricting the model here. The unconstrained is the model that contains a variable in it, which is H1. The full model is corresponding to H1. People sometimes get this wrong here and think that null means unconstrained. No, constraint is H0 because it fixes things to be 0, right? This is the one that says I will constraint here, this is equal to 0, and this is the one that says no, this is not 0. I can take it to be anything that the model tells me. So this is the unconstrained or the full model versus constrained or reduced model where some things are 0. And what this does is this kind of drop-in deviance test will compare the smaller model with the larger model. So the smaller model is the one, the null model, which says things are 0, and the larger model is the one that says things aren't 0. And so you can look at this. So this is earlier, as we were saying, the null model is where everything is 0, and H1 is where something is not 0. This is the kind of test it does. It doesn't test for individual coefficient. It does a model test, one model versus the next model. So here it says they're all 0 versus some of them aren't 0. I can certainly compare with all 0, and here they're saying some of them, at least some of them isn't 0, right, which is the full model. And so the deviance here represents the discrepancy between those two models. Which model is better? The one with the smaller deviance. And you can actually test for these things in the usual ways, in some ways. So we'll see the test in a second. But as I was saying earlier here, we saw earlier the differences. So if I look at this particular model with the interaction term, there is the null model which says everything is 0. And there is the full model which says that some things aren't 0 here. And so the residual deviance, of course, is smaller, as it always will be for a full model. But I want to see whether it's significantly different. So I want to compare this model, not with a null model, but with the previous model which didn't have the interaction term. So here, my full model is the one that contains the interaction term, and my reduced model is the one that doesn't. The constrained model is the one that doesn't contain the interaction term. So the way it works out is that the difference in deviances has an approximately chi-square distribution, and the degrees of freedom is equal to the differences in the degrees of freedom. And the difference in the degrees of freedom. So between the full model and the reduced model, because the full model has more variables, reduced has fewer variables. Look at what the difference in the number of variables is, the number of coefficients, and that is the degrees of freedom over here. And so if I'm looking at this interaction one, then my degrees of freedom is simply 1. And I'm looking at the deviances here for the unconstrained model, which is H0, where beta 3 is not 0, my interaction term is not 0, versus my previous model where I had the constraint that beta 3 was equal to 0. And so you can see that the constrained model has a higher deviance as opposed to the unconstrained or the full model, and the difference in the deviances is 3.91, and my degrees of freedom is essentially 1 here. So my chi-squared probability p-value comes to 0.048. Now that is less than 0.05 for sure. So the deviance test is a much rougher test than I'm getting by the p-value test, what's called the Walls test, for each coefficient separately. So it says it is adding something to the model, but it's not the best model nonetheless. And you can do exactly the same thing by this ANOVA command, ANOVA for those two models that are nested. So one model has a variable that the other one doesn't contain. One is nested within the other one. So in this case, my model which doesn't have the interaction term is nested within the model that does have the interaction term. So I've got a full model. Within that, I can take one variable out. I've got a nested model. And so this does the tests for me. It tells you the two models are actually fitted here, one with interaction, one without interaction. It looks at the deviances for each of those things. And so it looks, the difference in deviance is over here, the degrees of freedom is different by 1. And so you can see what's going on here. D of 42 here is for the unconstrained model, and 42 for the constrained, 41 for the unconstrained, one extra variable to fit. And so the chi-square probability is 0.048. That tells me that the model with the inflection term does add something, but it's not as stringent or as strong as the Walls test, which is where I look at p-values individually. So it's used for many reasons. I'm not going to use it very often myself here, but it's part of the course, so I'll show it to you. In some places it's useful here. Otherwise, usually by looking at p-values alone from the R-fitted model, you can decide what the best model is. Are there any questions? We've done a fair bit here today, but the main thing is fitting the models in R, looking at the output, and then interpreting them. First of all, in terms of odds ratios, and then secondly, extracting from that something you can explain to somebody else who mightn't know much stats, who mightn't care about the stats part of it. Now, in your next test, I think I've got a couple of questions along those lines of saying some things in non-statistical ways. So if you do that, you can't mention things like odds ratio, you can't mention things like p-values. I want something you can write in a line or so saying what is actually what you're seeing there. Yes, question? No? Just stretching. No questions, all good? Well, all right. I'm going to show you a short video of something. Next time around, we'll show a video on stats part, right? But this week, we'll have a bit of fun. So here we are. You see this before? Lovely. If you haven't seen it before, interesting for you, I hope.
Thank you. Thank you. Thank you very much. Take a seat. G'day, everybody. How are you? Before I start anything, I want to first of all thank you for the opportunity here to be a part of the Summer Conference 2006. For those of you who don't know me, my name is Nick Vujicic. I'm 23 years old, and today I want to share with you 3 main keys in my life that got me from a life without limbs to a life without limits. For those of you who do not know my story, I was born without arms and legs. There was no medical reason why this had happened. Today I just want to be real with you. I'm going to be in your face at times, and I'm not going to apologize for it, so buckle up. But before I do get into anything, I always love to share some funny experiences that I've had in my life. I love kids' reactions. Kids' reactions are fantastic. Like, I go to the shops and everybody just stares at me and stuff. You saw me in my wheelchair there on the DVD last night, and all the kids coming up and say, "What happened?" And I go up and say, "Cigarettes." And stay away from those cigarettes. Anyway, I have a lot of funny stories, but I love to do quite a few hobbies of mine, like, you know, I jump in the pool and I actually float like a life jacket, as you've seen on the screen. I bob up and down like this, and then have my little motor down here and go like this. When I go to like public like pools and stuff, all you see is this head flowing across the water like this. And kids freak out. But I went to South Africa on our tour in 2005 in February, and went to a water theme park, and for the first time I went down the water slide all by myself. I was very proud of myself. And obviously at the bottom of the slide there's a pool with people just chilling, just relaxing, chillaxing, you know what I'm saying? They mind their own business, watching others come down the slide, and here I come, they're all looking at me, and I was so tempted to look at myself and go, "What happened?" Pretty cool. But look, the funniest story I can tell you is when I'm in a car, obviously you have no idea that I have no arms, no legs. You just see my beautiful, sexy face. And we're at the red lights, and this car pulls up next to us. This girl's looking at me. And I'm thinking, okay, let's have some fun here. So I look at her, and I get her attention, eye contact, and I'm like, okay, this is what I'm going to do. I actually get my seatbelt in my mouth, loosen the seatbelt, and in the car seat, just do this. You should have seen her face. She was like, "You're freaking me out, man. Green light, quick, quick." I would love to. All right. Right there is good. Okay, wonderful. Now, joking, I don't need to run up. All right, you ready? Thank you very much. Take that. It's yours. No worries. One more trick before we get into my story. I have a phone up here, and what I'm actually going to do is I'm going to flick up my phone onto my shoulder. Now, this does not always happen the first time, but what happens when you fail? Very good. What happens when you fail? Very good. Can someone give me a sound for a ringing phone, please? Very good. Very good. Thank you. Thank you. Here we go. I'm coming! Hey. Is that cool? Beautiful. Beautiful. I want you to write down 3 things for me, please. I want you to, first of all, write down the word perspective. Perspective. And the word after that, I want you to write underneath it, vision. And then underneath that, I want you to put choices. So perspective, vision, and choices. This is what I'm going to be speaking about. I'm going to be real with you and start from the beginning. I was born...
This is on YouTube, you can look at this afterwards, but I just want to talk about the 3 things he said. Luckily for me, I actually met the man. I was in Griffith University some 20 odd years ago. He was there in a wheelchair at that time doing his degree in finance and management, double degree in accounting and finance actually, I think. So the 3 words he's talking about is perspective, how you look at things, how you view things. Do you think your studies is important for you? It's not important, it doesn't really matter, right? Then you won't bother too much with it. Like many students don't do. How valuable is it to you? What do you think, where will it take you? How important is it in your life? Perspective is very important. How you view others, for example, around yourself, your relationships, all those things are part of the perspective. The value system you have, what you live with, if you like. The next thing was vision. Now vision is a word that's banded around quite a bit, you see, because everybody, you have visions every year these days. To me, vision is something much more important and impactful than that. Most people will not have more than 1 vision in their lifetime. Yeah, I'm after something, vision is something that's massive and huge. It's like I keep saying, it's more like a dream, right? And if your dreams don't scare you, they aren't big enough. Simple as that. They're going to scare you. Can I do it? Will I get there? Those kinds of things have to be questioned within yourself before you get to the vision. So most people don't get a vision until they're much late in their life. But there are some young ones I've spoken to who get vision quite early in their life. So they'll go further because they have been focused, they get a perspective earlier than most other people do. And the last was choices, and I keep saying the biggest gift we have is choice. We can choose what to do. You chose to be here today. Many didn't choose to come here. You choose to keep up to date with material. Many will look at the thing. Was speaking to a student today who was saying that he's about 3 weeks behind. He's going to catch up on the weekend. Hey, why are you behind in the first place? What happens if I go behind? You ever thought of it that way? I have a life as well. I have things that are important to me as well. Yeah? Why can't I go behind? Misses the whole lot of you, right? You might say, well, you get paid. Yeah, I get paid. Sure. But you actually pay to do the stuff. You pay for it. And you still don't value it. You still don't keep up to date with it. Now, why not? This is your full-time job. I keep saying this. This is your job. This is the most important thing. It should be the most important thing. If it isn't important, I think you don't belong here. Simple as that. Hard facts of life. Now, I keep coming, sometimes I talk about myself. See, when I was in my honors year, I had just recently got married. 2 children below the age of 2. I was working full-time to support the family. I didn't miss a single class. That's the hardest year I ever had. But I was there. Yeah, I made it because it's important for me. So choices, the most important thing in life is choice. How you choose things, what do you choose? You've got a goal, a vision. How do you get there? The pathway to that, the timeline to that, and the choices you make along those lines. You know, our life is nothing more than a series of choices. What you see yourself as today is the choices you made in the past. We will go to next, the choices you make now and later as well. That makes a big difference to how you think of this. I think of life as essentially as parallel pathways here, and at some point you make a choice that takes you from one pathway to another pathway. I call those things knot points. There's a knot there, you've broken that line and joined to this one over here. Now, if you happen to make a wrong choice over here, then sometimes you're lucky enough to be able to come back again. But in my experience, that always is accompanied by 2 things, loss and pain. As an example, hope that doesn't happen to anybody here. You get married to the wrong person. You can recover, you can divorce him or her. But there's pain and loss. You've lost some time in your life, if nothing else. You'll make some other losses as well in emotion, whatever else, but there's pain as well there. Yeah, so you can sometimes recover from that, but there's always going to be some pain and loss there. But of course, it can be beautiful as well. It can make a big difference to what happens there. So when you have these not points in your life, know they are not points, first of all. Recognize them as not points. And then this is where you need to make a very informed and considered decision. Don't rush into it. Well, don't take forever, of course. Don't rush into it. Make the choices with the right kinds of mind frame and information. So, usually if you can't decide, make a list of the pros and cons. But that's not enough. You're going to weight each one of those, right? Weight them so you know which one's more important than others, and go with those things. The other thing is how we look at our lives, you see, because all of us, yeah, me too, have weaknesses, don't we? None of it is perfect here. What's his weakness? No arms and no legs. And yet, that's his greatest strength, isn't it? Because if I turn up to say exactly the same things, it doesn't have the same impact as when he says it. Isn't that the case? So he's turned his weakness into his greatest strength. Now, there are many other people in the world without arms and legs, unfortunately, or just without legs or whatever else, that don't have the same impact because they haven't made the same choices, right? They haven't turned that weakness into a strength. So turn your weaknesses into strengths and see how that goes, right? Turn them around a little bit, work on them, and you might find that what you thought was a weakness suddenly becomes a big strength that takes you places. So please find, if you're interested, here's a video on YouTube. It's there, the full thing there, several of those in fact, and look at them and see whether that has an impact on your life. That's enough for today, I think. Thank you. We'll see you next week.